Now let's consider another example where you can see formation of the band structure. This is so-called example of the weak periodic potential. So we have again Hamiltonian, which is a kinetic energy term, plus potential. And we consider potential as some kind of peak potential. So it means that we can introduce some kind of perturbation theory to find the corresponding energy spectrum. So the first step, at first we know that it's a weak potential, but it's periodic potential. So it means it has the following property. X, we consider again one-dimensional case, it's more easy to understand. V at x plus a is the period of the structure, is equal to V at x. So it means that we have potential of this profile. So it will be weak periodic potential, like that, with the period A. The definition that it is weak, it's a little bit non-trivial because we need to compare this magnitude of periodic potential with something, and we'll see exactly what is the meaning of this potential is weak later on. So for some conditions it's not weak, but for many other cases weak. Now let's consider what should we expect from this potential. So we know that without this potential we have just plane waves. So the energy spectrum is just p squared divided by 2m. So it's parabolic dispersion relation, energy as a function of momentum. So its periodic potential goes like that. Now the question is when we introduce, so this is just free electrons without any periodic potential, so we p squared divided by 2m. Now we introduce periodic potential, and this periodic potential will couple different states. So in the first approximation we can consider this one state with momentum, for example p1, it will be coupled to the state with momentum p2. The question is what is the magnitude of this coupling, how can you find this coupling? The coupling is determined by the matrix element. If you calculate this periodic potential, matrix element between these 2 points. Because the wave functions in this case for the free electrons, the wave function will be exponent I, let's call this kx. So k is a momentum divided by Planck constant, so in other words it will be I p divided by hx. So it's convenient describe this free electrons not in terms of momentum but in terms of the wave vector, which is a k divided by Planck constant, which is momentum divided by h. So it's a k. It has dimensionality of 1 over x because it's convenient to describe all the properties in terms of this wave vector. So we'll describe it not in terms of momentum but in terms of wave vector k. So we have 2 points k1 and k2, and I want to find the coupling between these 2 points due to periodic potential. Because this is the wave function is the plane waves, so we consider the matrix element between 2 states, k1, periodic potential, and k2. So it will be integral of exponent, this is the k1, so it will be exponent negative I k1x, v as a function of x, I k2x dx. So you can see we can combine these 2 exponential functions, so effectively it will be integral v I k2 minus k1x. So it means that to find the coupling between 2 states, we just need to find the Fourier transform of periodic potential with the wave vector q. Q is the difference between these 2 wave vectors, k1, k2. So let's calculate Fourier transform. Let's find the properties of the Fourier transform of periodic potential. So the coupling is determined by the Fourier transform and this wave vector k, wave vector q, which connects these 2 points. So let's calculate Fourier transform of periodic potential. So we can write down the periodic potential as a system of the following localized potential with the period A. So another way we can write down V as a x as a sum of potential. Let's call this V0. So it's each of them is a V0. V0 is a function of x localized at different points. So it's a just approximation how we describe this periodic potential, system of atoms localized at different points, and each atom produces very big perturbation, so very big trapping potential, for example, like that. So it will be x minus NA. And we calculate n from all points from negative infinity to infinity. Of course, n will be determined by the size of the system, because this system should have a finite size, so it means that it will produce some finite number. So it's not from negative to infinity, it will be within some finite number of states. So it means that this is a V0x, so it means that each profile will be V0x, and it will be localized at different points. This is exactly the meaning of this x minus NA. So this profile will be localized at point NA, and A is the period of this structure. Now let's calculate Fourier transform. So we calculate the integral x point I qx IQX, and we introduce similar to what we have for the wave function, because when you calculate the wave function we need to introduce the normalization factor. When you look at the wave function of electron in the free space, it will be x1 divided by square root of L, x point I kx, because the wave function should be normalized. If L is the size of the system in x direction, so the size, then the integral of c squared over x should be 1. That's why we need to introduce this normalization factor. And when you calculate the Fourier transform, it's a product of two wave functions. As a result, in this case, you need to put some extra factor 1 over L. Because the factor, when you calculate this, is a matrix element. Fourier transform determined by the matrix element of the between the plane waves. So we introduce this extra factor 1 over L. So let's call this V. So we calculate Fourier transform as a function of, it depends on Q, so the 1 over L integral V x exponent I qx dx. Then the next step, I substitute V in this form, so it's a sum over n, 1 over L, sum over n. Of course, it's not goes from negative 3 to infinity, it will be within some finite number of points because this system has a finite size. So to be integral V0 x minus NA x point I qx dx. Now we can introduce a new variable, y for example. We call this y, x minus NA. Then x will be y plus NA, and then the integral becomes the following: 1 over L, sum over n. So x should be replaced by y plus NA, so it will be y, and then NA is a constant, so we can move this outside of the integral, so it will be x point I, Q, and A. And this will be the integral over y, V0, y, x point I, Q, y, dy, or dy. So this is exactly the Fourier transform of a single profile of a single potential V0y, so it will produce some function of Q. So it will be some profile of this form, so it will be V0Q, so it has this profile, for example, like that. So it, of course it depends on the shape of this potential, and again it's some function of Q. It has some maxima at 0 usually, and then it goes to 0 some interval. So this is V0Q, but now let's look at this expression. So of course this expression does not depend on this integral of the Fourier transform of V0, because it's just integral over a single potential. Now we calculate the sum over n. And this function has the following property. And because n goes, roughly speaking, from minus infinity to infinity, this function will be 0. It will be non-zero only when q times a, q times n, you can see we have q times n times n. And q a is equal to 0, for example. If qa is equal to 0, then it will be exponential part will be 1, and it will be the sum over n, it will be total number of points. Okay? If qn is equal to 0, then sum over n over 1, it will be total number of atoms in the system. If qa is equal to 2 pi, look at this expression, qa equals 2 pi, it will be I n 2 pi. Again, it will be 1. Exponent is above I n 2 pi, it will be 1. So again, the sum will be n. If qa is equal to 2 pi times m, any integer number m, we have the same property, qa 2 pi times n times m, it will be 1. So again, the sum will be n. If we have small deviation from this condition, then the sum will be 0, because it will be the sum of many periodic functions, and it is possible to show that it will produce 0 expression, 0 value. So effectively we have some kind of sum will produce some kind of delta function localized at different points. So what we have in this expression, now we can combine this property and we can write down the following expression. Sum of n exponent I, q, and a will be equal to sum of m, n is the number of atoms, delta, q, and qa minus 2 pi m. Or we can write down q minus 2 pi a. And then we divide by, if you move this, so we can write as a q a 2 pi n, or if you move this, if you divide by a, effectively it means that you need to divide by 1 over a. Here. The properties of the delta function. So you can see that the Fourier transform of the periodic potential will be non-zero only at the discrete values of q. So it means that V 0 will be, of course, when q is 0, so it doesn't matter. Q is 0 doesn't so important, because q0 means that it will be a matrix element between the same states. So it's not, we don't need to consider this case. So the first non-zero element will be when q equals 2 pi over a. Then the second will be 4 pi over a. Then next will be 6 pi over a. So q is 2 pi m over a. So this at this point, at this values, Fourier transform, the periodic potential will be non-zero. Then we need to multiply by Fourier transform of the of a single potential, single localized potential, by this factor. So it means that Fourier transform will be non-zero only at the discrete values, only at these values of periodic potential. So it will plus minus. M can be positive and negative, so it will be positive and negative. So it will be 2 pi over a, 4 pi over a, 6 pi over a, negative 2 pi over a, negative 4 pi over a. So we have non-zero values of periodic potential only at these points. At all other points, the Fourier transform of periodic potential will be 0. So it's the main property of this Fourier transform of periodic potential, and it's a very general property. Consider Fourier transform from any periodic function, and then it will produce only non-zero values only at the discrete points. So this is the property of this Fourier transform. So now we take into account this property. So you can see we have the Fourier transform non-zero only at this point, so we don't need to consider this region. Of course, we have non-zero Fourier transform of 0q, but again, it doesn't matter because it will produce, it will be just a matrix element within the same state. So only at this point we have non-zero Fourier transform. Now, what is the meaning of this fact that Fourier transform is non-zero for periodic potential, is non-zero only at the discrete points? Now let's return to our energy dispersion. So we have 3 electrons at first. So we have parabolic dispersion relation. So it's E as a function of k. So it will be k squared h squared divided by 2m. And we have the coupling between two states, k1 and k2. So let's call this k2, this is k1. The coupling between these two states will be non-zero only when the difference between k2 and k1 is equal to 2 pi over a times integer number. So when it is equal to 2 pi over a, 4 pi over a, 6 pi over a, and so on. So it means that the distance between these 2 points, q2 minus q1, should be equal. So at first we consider the strongest matrix element, so which corresponds to 2 pi over a. So this difference should be 2 pi over a. Only between these 2 points we have non-zero matrix element. So if you consider, for example, q1 and this point q2, because the distance between these 2 points is not equal to 2 pi over a, the matrix element will be 0. So between these 2 points we have only non-zero matrix element between these 2 states. Then if you look this point K2, then it will be coupled to another state at the distance 2 pi over a, which has this energy. So and so on, and this direction it will be again 2 pi over a, it will be coupled to the state. So it means that we have some discrete points, and we have the coupling between all these discrete points. And we can consider if periodic potential is very weak, we don't need to consider coupling with all other states, because it will be coupling with another state with a difference distance 2 pi over a. You can consider only coupling between the nearest states, k1 and k2. And in this case, if effectively we consider only these 2 states, and the coupling between these 2 states is determined by this Fourier transform of the periodic potential 2 pi over a. Then we can consider what is the effect of such coupling. So it means that we need to construct the matrix. So it will be only 2 states, and we have the coupling between these 2 states determined by this periodic potential, which is determined by the Fourier transform at this point. So another way to find the corresponding energy spectrum, we need to construct the matrix. It will be 2 by 2 to find the energy of the system. The first will be energy at k1 squared h squared divided by 2m. And then we have the coupling with another state, will be h squared k2 squared divided by 2m. So let's call this E1, E2. So the energy of this state will be E1, this one. The energy of state will be E2. Let's call this E1, E2. And we have the coupling between these 2 states, which is determined by the matrix element. Let's call this V1. V1, which corresponds to this point. So it's V1. So we can write down, so this is a free electron states, and we introduce the coupling between these 2 states by the matrix element V1. Then from this equation we can find the corresponding energy spectrum. We just need to diagonalize this matrix 2 by 2. Again, we consider only 2 states. Of course, there are many other states, but you can see they have a much larger energy. So the effect on these states will be much weaker if we have a weak periodic potential. So from this expression, we just need to find energy of the system. So we need to find the eigenvalues of this matrix. So it will be E1 minus E times E2 minus E minus V1 squared should be 0. Then from this equation we can find that E will be, what is this? So it will be E1, so you can diagonalize this matrix plus E2 divided by 2 plus minus, so it will be 2 energy levels plus minus square root of E2 minus E1 divided by 2 squared plus V1 squared. So you can easily diagonalize this quadratic equation, so it will produce 2 energy levels. And at first we can see if V1 is much less than the energy difference between these 2 states, then the effect will be very, very small of this periodic potential. So if E1 is much less than this energy difference, the effect will be very small. The only strong effect we should expect when E1 is very close to E2, when they have almost the same energy. And in this case, this will be almost 0, and then we'll see it will be very strong effect. So you can see we cannot disregard this coupling. So it will produce 2 energies. E1 will be equal to E2, so it will be E1 plus minus V1. So it will be a very strong effect. Initially we have almost degenerate levels, E1 and E2. When you introduce this coupling between these 2 levels, it will shift one to V1, another minus V1. So we have strong effect. So it means that these 2 energies should be the same. And how can, at the same time, the distance difference between this K1 and K2 should be 2 pi over A. So it means that we need to consider one case special case when you have very strong coupling to this very big periodic potential. So this case when energies are the same and the distance between these 2 points is 2 pi over a. So it means that this point will be pi over a and this will be minus pi over a. The distance will be 2 pi over a and they have the same energy because the energy depends on the k squared. So in this case the coupling between these two states will be strong because they're degenerate states. And this coupling introduces the gap in this case. So if you solve this equation, if you consider just points very close to this degeneracy point, you can find the following dispersion. How this energy dispersion will be modified by this potential. It goes like that, and this goes like that. And we have the gap. We have the region of energies within which you don't have any energy, which you don't have any solution. We don't have any states. So it goes like this. So in this way, we can introduce a gap in this energy dispersion. So initially, for all energies, we have some solution. But when we introduce such coupling, when these energies, two states are degenerate, the effect of such very big periodic potential will be very strong. And this effect, this strong coupling introduces a gap in this energy dispersion. So this is the effect of this very big periodic potential. And in this way, you can see it will produce some band structure. So it means we have one band. Then it will be another band. So let's look in more details formation of another band. So we have minus pi over a, pi over a. So we have strong coupling between these two states to introduce the following dispersion. So it will be goes like that and goes this direction. Then we have 2 points, another 2 points, this will be 2 pi over a, and this will be minus 2 pi over a. Again, we have strong coupling between these two states because they are degenerate, and the distance between these two points in k space will be 4 pi over a. So again, at this point, we have non-zero dipole matrix element. It will be weaker than V1, let's call this V2. So this gap will be of the order of 2V1. So it will be shift one energy plus V1, another minus V1. Then we have strong coupling in these two states. Again, to introduce the gap like that. And the magnitude of this gap will be of the order of 2V2, which it will be smaller than this one, because you can see it becomes smaller and smaller, the Fourier transform, and so on and so on. Then it will be another gap. For k, it will be 4 pi over a, then it will be 6 pi over a, and so on and so on. They degenerate states, and at each this degenerate state, and then you can have the coupling because of this matrix element to reduce the gap in this structure. So finally, we have the band structure. So we have one band, then you can see we have another band, then we have gap, 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 and so on. So this is how illustration, how we can introduce band structure in this very big periodic potential. And so we have initially we have 3 electrons, introduce very big periodic potential, which produce very strong coupling between the only discrete energy levels, only between these energy levels or between these energy levels. As a result, can produce the gap. Because if you have the coupling within for all Q, then we don't have, it will be just change the energy levels of all this dispersion. We don't introduce the gap in the system. Only because of the periodic potential, we have the discrete values of Q at which the matrix element will be non-zero. As a result, we introduce discrete set of key points for which we need to have strong effect of this periodic potential. So this is an illustration how we can introduce the band structure within the weak periodic potential, and this is called the so-called nearly free electron approximation. And of course, in this case, we cannot produce correct energy energy dispersion for many materials, because in many cases we have strong periodic potential, so the effect of such periodic potential will be strong for all states, but at least it gives some idea what happens in the system. And we can use this approach if, for example, we produce some kind of artificial solid, build some artificial solid which have some very big periodic potential. Then we can use this type of method to study the properties of the state very close to the edges of the bands. We can find, for example, the effective slope and so on. We can find the effective mass at this point, and so on and so on. So again, this is can be useful only when you have not the real crystal, but for example, when you have some artificial crystal, when you introduce some very big perturbation to the free electron motion, which is a periodic potential. So we can describe, we can use this approach to describe the properties close to this band gaps, band edges. Another method which can be used to identify some band structure, and this method is used a lot in many calculations. This is so-called time-binding method, because this is more appropriate to study the properties of the real solids. So this method, let's look at the basic elements of this method. So this is a method when you have the strong periodic potential, and then we introduce, in some sense, we consider the kinetic energy term as some kind of perturbation, and try to find the corresponding energy spectrum. So time-binding method. So the idea of the time-binding method is that so we have periodic potential, like that. Then for each quantum well, we have the set of energy levels. So at first we consider this a strong periodic potential. So at first we consider a single quantum well, then another single quantum well. For each quantum well, without any coupling between the wells, we have the energy levels. And then we assume that this distance between the energy levels is relatively large. And in this case, we can consider the coupling only between the states with the same energies. So it means, of course, the wave functions will be localized at this quantum well, but it has some finite decaying length, so it goes like that. So we have the overlap of these wave functions within this region. As a result, we have some kind of effective coupling between the states localized at different quantum different wells, different atoms, for example. You consider this is some kind of system of atoms. For example, this can be s orbital, 1s or 2s, or in other ways this will be, for example, 1p, or for example, higher order orbitals. For example, this will be 3s, this will be 3p orbital, and so on. It will be and so on, and we have the coupling between the corresponding orbitals. So initially they degenerate levels, and the coupling is introduced because we have the overlap between the wave functions. And this coupling can be described in terms of the effective hopping of electrons from one well to another. So electrons will jump from one well to another, and we can effectively describe this jump as a propagation of electron along this chain of atoms. So this is the idea of the time-binding model. So let's consider the main elements of this time-binding model, at least how can we find the corresponding energy levels. So when you consider this time-binding model, of course there are different approximations which can be used to find them for different time-binding models. So we can, for example, consider only one level within at each atom, and consider coupling of this level at different atoms. Or we consider, for example, two levels at each atom, and then we consider coupling between these two levels. So it means that we have the coupling between this level and this one, between this and this, this and this, and so on. So it will be something like that. So it depends on the energy difference between these two levels and how strong the coupling between different levels is, and it depends what type of approximations we need to use. We consider the simplest approximation when we have only one level at each atom, at each well, and let's write down the corresponding Hamiltonian. So let's look at the corresponding equations.